We've already looked briefly at the infinite series and why it can only be geometric. We've shown why it cannot be arithmetic. By the end of this video, we're going to fill the formula into this block. Let's just look again at the test for convergence. These are your rules to learn. If r is less than 1 or greater than -1, it will be converging. That is to say, the sum of the series will converge to get a number, the infinite series. So that is again to say, the sum of the infinite series will converge towards an integer. If r is less than 1 or if r is greater than 1, this means it will diverge. This is to say, an infinite series will not give us a sum, or it will give us a sum. The sum will be plus or minus infinity. Let's have a look at this test. We know previously that the sum of a finite geometric series, where there is a last number in the series, in this case n, is equal to a 1 minus rn over 1 minus r. And this is an equation you would already have learned. We are only concerning about ourselves about where r is converging. That is to say, where r is less than 1 or greater than -1, as we've done here. Let us take a number, r is equal to a half. In r is equal to a half, it fits inside this bracket here. So we're just going to show you something that can happen when we take a number in the middle here. Let's take n equal 1. Let us look at this term here. This is the term that is of interest to us. What happens when we make n equals 1? We know that goes r to the power of 1. We let r equal a half. So we know it's going to be a half to the power of 1, which is a half. Great. Let us take n equals 2. Here now we've said n is r to the power of 2. And we know r is a half. So it's a half to the power of 2. We square the top, we square the bottom, we get 1/4. Now let's look lastly at n equals 3. We have r to the power of 3, which is the same as a half to the power of 3. Square take the cube root of the cube of the top and the cube of the bottom, and we get 1/8. What do we notice here? As n is getting bigger, what is happening to our r over r to the power of n term? So what we notice is that as n increases, r is in fact decreasing to 0, because we know that an eighth is smaller than a half. And this will continue as we go to greater n's. So now, what we're going to do here is make this. What happens is, as n tends to infinity, which is now just this n, tends to infinity. That is just to say, as n gets bigger. We're drawing our infinity here, which is our sideways 8. So what we said, as n tends to infinity, as n gets bigger, r to the power of n tends to 0. That is to say, gets smaller. But what it actually means is, if we had to take this n and keep going in bigger and bigger and bigger and bigger, this number here would eventually get so tiny, it would tend to 0. So we know that it will never reach infinity or never reach zero, but this is what we say it tends to. So what is happening to this whole term? This whole term here is becoming a big fat 0. So what does that mean? Let's have a look at this equation. The sum to infinity of a geometric infinite series. This here is incorrect. It's meant to be infinity. Why? Because we're going from I equals 1 to infinity. We're saying AR, I minus 1, this is our normal equation, is A. Now what we had here is 1 minus 0. And that's obviously equal to 1. And 1 over R. And this is our sum for an infinite geometric series. We can now fill that in the block. And well done. There we have it. The complete sequences and series equations that you need to know. Great.